back to equivalence. Okay, going back to our example of investing $1,000, an individual would be indifferent between $1,000 today and $10,285 40 years from today. In this world where the interest rates are 6%, no risk, just looking at the time value of money, why would you be indifferent between $1,000 today or $10,285? I offered you $1,000 today or $10,285.72, and you took the $10,800 and you decided that you wanted the $1,000 today. What would you do? Borrow. You'd borrow $1,000, and how much would you owe 40 years from now? You'd owe $10,285. And how would you pay that off? I'm going to give you $10,285 40 years from now, and I give you that. What are you going to do with it? Or if you take the $1,000 today and you don't want to spend it, you'd rather have the $10,285, you put it in the bank. So either way, if I was to give you either one of those, you'd be indifferent. Both give you the same opportunity. In this world, basically allows you to borrow or save money at 6%, and there's no risk. If you don't mentally engage in this and understand that these numbers are equivalent, from here on out, you're always going to be in a shadow. That's what we're going to be doing in the time value of money, is converting a sum of money in one period to another, and if we do it correctly, we're indifferent. Okay, looking at the future value of $1, looking for an equivalent amount in the future, $1 today. So you see that today, $1 is worth $1. But over time, all the way to 40 years, you see that it grows. And it grows geometrically. And the reason it grows geometrically is because the interest is added to the principal, and you earn interest on the interest. Over time, you're earning more interest, and thus you see it growing geometrically. Now, just as a kind of a regression, I promised I'd mention simple interest as opposed to compounding. Simple interest is that over the length of time that you're earning interest on that principal, you're only earning interest on the principal. You're not earning interest on the interest. So when we want to find out how much money we have in our bank with simple interest in end periods, we have our principal. Each year we're getting interest on the principal. And if we keep that for 40 years, then the interest over that 40 years is just the interest on the principal 40 times, which is different than compounding, because in compounding, every conversion period, you're getting interest on the interest. In simple interest, you're not. You're only getting interest on the principal, the initial principal amount. This can be rewritten in this form. Interest is only paid on the original principal. No interest is paid on accrued interest. And my last statement in this, however, is in today's world, the compound interest is more common. And just as a comparison, so you see that compounding makes a big difference, you can see that on simple interest, the growth of your money is linear, because each year you're earning the interest only on the principal. Whereas you can see with compounding is geometric, because you're getting interest on the interest. Also, I wanted to show you graphically and visually the effect of time, the level of the interest rate on the future value. This is relevant as you look at, for example, retirement or investing money for a longer period of time. For example, if you could put in $1 million in retirement today and you earned 3% interest over 40 years, when you went to retire on that 3% growth, your $1 million would have grown to about $3.5 million. But if you put that $1 million in an investment portfolio that averaged 6%, and you went to retire in 40 years, instead of retiring with $3.5 million, you'd be retiring with over $10 million. Now, 3.5 versus $10 million, in my book, is a lot of money. Only the difference between a 3% return or a 6% return. Okay, now, of course, you may not start with $1 million, but even $1,000 or $100,000, you can see that investing at a higher rate for a longer term period of time with compounding, investing at 3% versus 6% makes a big difference. Now, why is that relevant? If you plan on investing your retirement solely by putting your money in money market and CDs, where you're earning on the average 3% per year over the life of your portfolio, versus a more aggressive portfolio in the stock market, where there's more risk, we talked about that, But on the average over that period of time where you're earning over 6%, you can see that it makes a big difference at the end on the kind of retirement or wealth that you've accumulated. Also notice, however, that if you start your investment when you're 50 and you only have 15 years left, notice how little your money's going to grow. And look how much it's going to grow if you invest in the long term for 40 years. So is there any reason now for you to start thinking about, when you finally get your degree, to start putting aside money for to accumulate wealth and to let it grow? Because you can see it's going to make a world of difference if you accumulate that wealth over 40 years as opposed to waiting and only having 10 to 15 years to accumulate wealth of which to retire. I mean, you probably intuitively realize that, but you've probably never seen it graphically at the magnitudes of the difference. Another problem, how many years would it take before you had $80,178 in your bank account if you deposited $25,000 today in a bank that pays 6% interest annually? So we're turning this problem around a little bit, and we're going to say, basically, I have $25,000 today. You just inherited $25,000. You go out and buy a brand new Chevy truck, or you can put your money in a bank, draw on 6% interest, so that you can buy your Porsche. So we can look at our timeline. Today, we put $25,000 in the bank. We want to draw $80,178 to pay for our Porsche. The bank is paying 6% interest. The question is, how long do we have to wait before we can get our dream car? In this particular problem, we see that we're dealing with a single sum of money, and we see that we're going to the future. So we can use the future value of a single sum formula. In this particular case, our future value, we know, is $80,178. Our present value is $25,000. Our interest rate is 6%, and we're trying to calculate the M. So you can see, I didn't scribble too much there, you can see how those connect. So we pull out our calculators again. Well, first of all, for you mathematicians, you can solve for this, and you would do that by dividing both sides by 25,000 and then taking the logarithm of both sides. So you can do this particular one by hand if you want. Your calculators will also handle it, as you can put 6% I, 25,000 PV, zero out your payment, put your 80,000 as your future value, compute your N, and it comes out to 20 years. So it will take you 20 years, and so your decision is that you may not want to wait 20 years for your Porsche. You may want your Chevy truck today. So the question is set up, what interest rate would a bank have to pay on a $25,000 deposit if you wanted to withdraw $64,843 from the bank account in 10 years? In a lot of these problems, and you'll find in the homework as well, the verbiage gets all tangled up and you wonder, what are you really asking for? That's where we do the timeline. And you see in this case, again, we draw the line. We're at time zero. We deposit $25,000 into the bank. We want, in 10 years, we're withdrawing $64,843. The question is, what is the interest rate? Okay, in problem 1, 2, and 3, notice that we're using the same formula, the future value of a single sum formula. In this particular case, we know the future value, and we know the present value, and we know the number of periods. What we don't know is the interest rate. Now, for you mathematicians and purists that want to do this through arithmetic, you're going to divide both sides by 25,000, and you're going to take the 1/10 exponent of each side, and the problem will fall out. Or you can rely on your financial calculators. You're going to put 10N, a $25,000 present value, zero out the payment because we're not dealing with annuities yet. The future value is $64,843. We plug this into our calculator, and the rate comes out to 10%. Part of the reading for this lecture, if you recall, was a newspaper article, De Haven. Again, you could find that, if you didn't, up on the 330 web page. Off to the side there's readings, then you would look for that particular reading. I've summarized this newspaper article. And what this article reports is that in 1777, Jacob de Haven lent the Continental Army $450,000 in gold and supplies. And that's in your handout on War Financier. Goes on to say, as we all know, that the Continental Army won the war because we're the United States of America. But what you may not know is that the Continental Army, being in financial difficulty, never paid back that loan. It turns out he died childless and in poverty. And because he didn't have any children, that was basically, the family didn't worry about that debt. But in 1989, some descendants, probably from one of his brother or sister, can't remember which, one of their descendants filed a lawsuit. They probably took a class like this in recognizing the time value of money, or they're in law school and recognizing the power of lawsuits, I'm not sure which. They filed a lawsuit for the repayment plus interest of this 212-year-old loan. Seemed like a reasonable thing to do. The Continental Army owed the money, and probably back then that was a lot of money and may have made the difference between winning that war and not winning the war. So it makes sense that we today should repay that loan. Well, they filed a lawsuit, and of course the lawyers have to get together, and the lawyers use expert witnesses. Knowing that you've taken this class, the lawyer for de Havens hire you at $100 an hour to figure out what the appropriate amount of money should be. Okay? Now, I want you to use your intuition here. Okay? Before calculating it, how much do you think the government owes, the government, you and I, owes the de Havens after 212 years of having this loan, and particularly if we assume that interest is accrued at 6% compounded annually? 20 million? 40 million? How much money does the government owe de Haven in 1989 under the assumptions that we just listed? Okay, to figure this out, you're going to have to take this source of information and write it as a timeline. We have 1777 as our beginning point, 1989, that's when this article came out. We're saying that de Haven put up $450,000, gave it the cash outflow to the Continental Army. The question is how much in 1989 does the descendants of Mr. de Haven get back? First of all, which formula do we use? Recognize we're dealing with single sums of money, right? So we're going to use a single sum formula. Notice that we're going from left to right. We know the present amount. We're calculating the future amount, so we're going to use the future value of a single sum of money. Now, in this particular case, because the time reference is not 0, we're going to use the more general formula. In the number of periods, which is big N minus N, our big N is 1989. Our little n is 1777. The difference is 212 periods. So this loan has been accumulating interest for 212 years. Okay, this present amount was in 1777, and that was $450,000. We're assuming 6% as our interest rate. Now let's use our calculator. Okay, the number of periods is 212. The interest rate is 6%. The present value is $450,000. Zero out the payment, and we're going to compute the future value. And we plug it into our calculator, and it comes out to be $104 billion. So now, as taxpayers, wanting to honor the contract of the de Havens that made it possible for us to have the freedoms that we have, are you willing to give the descendants of Mr. de Haven $104 billion? You, as an expert witness, that's the number that you give the lawyers. And they've paid you a sizable sum to come up with that number. As it turns out, I didn't see this article again, so I can safely assume that the judge threw it out for whatever reason, maybe because there's not a direct descendant, or because the U.S. government was not liable for the Continental Army. The point here is to show you that this formula is used, can be used, and also to illustrate the importance of compounding. Because over a 200-year period of time, and there are real-world examples where this comes up, sums of money increase dramatically with compounding.